Okay, guys, let's get going again. So just before we start back up here, who has a question that they'd like to address in the final half an hour? Does anybody have a question or topic for discussion in the final half an hour? Irene? What's that?
It'll probably take 2 minutes.
Okay.
Yeah.
You got something? You got something? 1, 2, 3, 4, 5. Okay, good. Don't be shy. I've set aside time for this. Okay, because I'll just keep talking right up until the end if we don't have questions. So please think of some questions. All right, so great. So we'll leave about half an hour for that because I think we have about 5 or 6 questions to address. Perfect. Okay. So we've covered some stuff about inferential frameworks and ways to use neuroimaging to ask different sorts of questions. Now, typically this evokes a little bit of heated discussion from an audience because some people object to the notion that you can use fMRI to ask questions in certain ways or don't like some of the assumptions that I've suggested here. So there's nobody here who wants to take issue with that or discuss that kind of. I'm spoiling for a fight. No, really, is there any kind of further discussion or questions that people might want to ask about the ways that you can use neuroimaging to ask different sorts of questions? Does anybody have? Yes?
I guess just a couple of other methods that I've read some papers recently.
Okay, good.
People using correlational methods. So if you have an area of the brain that there's strong evidence involved in a certain process and another area that you don't have that strong evidence for, looking for correlations between activation of those two areas. And then using habituation, like if you think a certain population of neurons is responding to a certain stimuli, if you present that stimuli repeatedly, the signals go down.
Great. Okay, perfect. Thanks. So the questioner provided a couple examples of other sorts of ways that one might use neuroimaging besides just looking at raw levels of neuronal activity at a location. Okay? So some of those things are, what if I may, broaden that out to be effective connectivity. And these are methods which attempt to look at the relationship of neuronal activity at one location in the brain to other locations in the brain, right, as it varies over time. So that is there time-varying effects of neuronal activity in one area that is explained by neuronal activity in another area? And then another method is an adaptation method, or habituation, which aims to look at the effect of stimulus repetition upon neuronal activity in an area, and stimulus repetition and then recovery from suppression after repetition, right? Would those be the two broad categories? Right. Let me see if there's any I want to add to that. That's probably a good start. So what about these things? How do they fit into that framework that I've just sort of elaborated? Well, what I would say is that both of these methods are just simply other ways of measuring some parameter of neuronal activity, measuring something about neuronal activity, but yet they fit into the same 3 inferential frameworks that I wanted to provide in the very beginning. So taking them out of order, let's look at adaptation or habituation first. I should first of all say that this is a very powerful inferentially very powerful method for studying cognitive operations using neuroimaging techniques. Here's the basic idea. You present a stimulus, and then you present the stimulus again, either changed or unchanged in some way, and you look to find a decrement in neuronal activity. So the principle by which it operates is the following. If you look at early sensory cortical neurons, right, so particularly in perceptual areas of the brain, and this work was originally done in monkey studies. So if you have, a macaque brain, and you put your electrode down here in inferior temporal cortex, okay, and you present a picture of an object, say a face or something else, a toothbrush or something, and then you present that same picture again. You present that identical picture again, and you measure the neuronal activity that you get for this first response, and it's brrr, and the second response is brrr, and then the third time you present that exact same picture, it's brrr. And the fourth time, really not much at all. But now you present like a completely different picture, right? You get a recovery from the suppression, okay? And the notion is that these neurons adapt to the repeated stimulus presentation and habituate their response. They reduce their response until eventually you present a different stimulus, and then there's a recovery from adaptation, okay? And a lot of work has been done under, how frequently you have to present these stimuli, how rapid a decrement do you get, and How long do you have to wait to get this maximal recovery from suppression and all the rest? But if we just take it as sort of a general principle of a lot of these perceptual areas of the brain, that they evidence this kind of adaptation, that there's a reduction in firing for repetition of stimuli, this provides you with a sort of an inferential wedge that you can get in there to try and separate some of these different mental operations. And here's how. So imagine now that I modify this a little bit, and I say that, OK, well, I'm going to have this different face in these different circumstances, but I'm going to add something to these faces. I'm going to add visual noise. Just speckled visual noise. Okay? And what I find is for this IT neuron, as long as you can still sort of perceive the face that's underneath this perceptual visual noise, and the perceptual visual noise is different, I should say, it's important. It's different on each of these trials. So it's the same face, different visual noise on each trial. Right? Nonetheless, you see this decrement in response that finally recovers. But if instead you put your electrode here in early visual cortex, okay, you'll find that the addition of this visual noise eliminates the suppression. Instead, up here, it's sort of the same response every time, which suggests to you, or might suggest to one, that this area of the brain is abstracting away the underlying object that's in this noise and trying to ignore the noise, right? These neurons don't really care about the noise that's on top of it. They're being adapted by or responding to that object, that face that's being presented. Whereas these neurons here are actually responding to the entire visual stimulus, noise and all. Okay? So by looking at what a neuron adapts to, or to what a neuron adapts, will tell you something about the computational properties of that neuron. What is it that it's actually processing? This would tell you that these neurons down here are processing something more about object identity, and these neurons are processing more something about the luminance and just basic qualities of the stimulus. Okay? Does everybody follow that as a mode of inference? So in neuroimaging, this can be done as well, and with quite a bit of success. So for example, an early study, just since I'm familiar with the literature from sort of face areas, I'll talk a little bit about that. If you measure neuronal activity from the fusiform face area, and you present a face, and then present that face now rotated a little bit, and now present that face in a profile. God, I'm a terrible artist. And so you present a face, sort of the same person repeatedly, just rotated, and now you present a completely different face. All right. What you'll find is that there is an adaptation within the fusiform face area for the same face just presented in a rotated orientation. Okay? Whereas in other areas, perhaps in early visual areas like area LO, this produces the exact same response every time. What does that tell you? Well, that suggests that the fusiform face area is abstracting away the identity of the face independent of the orientation to which it's presented, which is kind of exciting. I mean, that tells you that neurons there are computing something about facial identity in sort of a 3D representation. Okay? So it's abstracting away this sort of 3D representation of the face, whereas neurons here in area LO seem to actually care about the particular orientation that the face is in. Okay? So it's a way of learning something about processing in those areas of the brain. I would argue that used in the way I've just described here, this is really an implementation type experiment. You're trying to learn something about, what is the implementation of face processing at these sorts of locations. You could also imagine using this sort of experiment as a localization type experiment, which is where you say, I'm interested in which areas of the brain process face identity. So I'm going to present stimuli which are either, I present a face repeatedly, or I present a face and then other sorts of objects, or a face in different patterns. And the area of the brain that shows adaptation to repeated presentations of objects, or of faces rather, but does not show adaptation to other sorts of repetitions, say repetitions of textures or repetitions. I drew a bad example here. Suppose I do repetitions of a particular face, and I also do repetitions of squiggly pattern lines, and repetitions of pictures of household objects, like an old-style telephone. Okay, so I present a telephone repeatedly. If I find that this area of the brain shows adaptation to faces, but not to this other stuff, I'll conclude that this is the area of the brain that does face processing. Okay, so that's where it's being used in more sort of a localization manner. And you can even, I'll leave it as an exercise to the audience, to then imagine a way that you could use adaptation to do an evocation type inference as well. Okay, so that could be done as well. So adaptation habituation is just sort of like a method, a way of measuring neuronal activity, which can be used in the service of any one of these inferential techniques. And I think that as a method, it's very powerful, and one that I'm employing in some experiments of my own right now. Okay? Any other questions about adaptation? There's a lot of really good review papers out there about it as a technique, if anyone wants to go read about it. Okay, effective connectivity. So this is the notion that neurons are actually connected to one another in the brain, which is not such a radical concept. So we've talked about, for neuroimaging data analysis, that we take the data from each voxel independently, right? We say, okay, here's the data, here's the data from voxel number, 107, and its data looked like this, and so there's a t-value here, which is 3.4, and now let's take a look at this next voxel, and here's its data. And so each voxel is analyzed completely independently of the other one, okay, in what's called a massively univariate manner. Univariate meaning we just take one thing at a time. But some have pointed out that there's actually some white matter that's connecting together different areas of the brain, and that understanding how different areas of the brain and their signals interact with one another might provide for further levels of inference or let you learn something else. For example, it might be the case that you find out that when neuronal activity, when you're, so a classic example of this is a Kristen Buchel paper, when you're performing a spatial location and object location learning task, right? So stimuli are presented, so you have a screen, and stimuli are presented at different locations, right? It might present, an apple at this location, and there might be, I hate questions which make me draw pictures. So, and then present a house at this location, right? So, imagine that in one version of the task, you just need to learn what the objects are. You have to remember an apple and you have to remember a house, right? And in another version of the task, you have to remember this location and this location. And then yet in a third version of the task, you have to remember apple at this location, house at this location. Okay, so you have to remember across a delay or for later recall the specific object at a specific location, right? In effect, joining together the what the object was with the where it was located. And as many of you are probably aware, there's this general finding that the dorsal areas of posterior and even frontal cortex are concerned with where objects are in space, and more ventral areas are concerned with what objects look like. And what Christian found was that when subjects were actually doing the what and where learning condition, that areas that are active in inferior temporal cortex and in parietal cortex during this task have an increase in the correlation of the neuronal activity between the two locations. Okay? That is, if I measure neuronal activity at this location in the parietal cortex under the learning of where the stimuli are alone, there's a certain amount of neural activity, and it's not highly correlated with down here. But when I look at the neuronal activity of these two locations when you're doing both at once, there's a stronger correlation of the neuronal activity between these two locations. Okay? And so this leads to the inference, in his case, that part of what is mediating learning of and linking together of object and location is increased communication between dorsal and ventral areas. Okay? And then you can imagine sort of further instantiations of this kind of inference. So the actual, yes?
Can you do this post hoc, or do you have to actually design your study?
No, you can do a post hoc. Yeah, you can do a post hoc. There, I should say, the actual details of doing an effective connectivity analysis are fairly complicated. And one of the main complications I'll just mention now is that you want to look at the correlation between regions of the brain, but you don't want that correlation to be driven exclusively by your task, right? So if, for example, this area of the brain is only activated when subjects regard where information, and this area of the brain is only activated when subjects regard what information, and there's only one condition that produces what and where activation, then, it's no surprise that these areas are then correlated in some sense if you just looked at the activation in those two areas, right? Because when the task evokes both activity in both areas of the brain, then naturally the correlation will have to increase between them if you calculate correlation in terms of that activated response. The more subtle inference actually that's going on here is you're looking at the correlation of signal at these two locations after you've removed the activation component, sort of all the leftover variability in the signal, right? The correlation of basically the error terms at these two locations goes up while you're doing those two things. Okay? It's not just the activation is correlated between the two, but the actual noise that's present in the data is correlated between the two. And that's the sort of the more subtle inference that's drawn in these cases. And to do that kind of sort of analysis just requires a little bit more work and statistical setup. But yeah, there's great stuff. I should say VoxBo does not have any effective connectivity methods built into it. And right now, those who are interested in doing it probably have to go to SPM, which is probably the best developed set of techniques that exist. And currently, the state of the art is something called dynamic causal modeling, which I once tried to read this paper. It's really hard. It's really hard stuff. So I would recommend that you sort of look at the SPM help groups and sort of ask questions there, and don't ask me about it because I really don't know. I'm hoping one day to recruit a graduate student or a postdoc who knows dynamic causal modeling who will come and teach to all of us because I can't figure it out. Okay. Effective connectivity as a mode of inference in general is used in sort of an implementation type flavor where you say, I'm interested in, I know these are the areas of the brain that mediate these mental operations of learning, where something is and what something is. And I just want to learn a little bit more about how they're connected and how they work together. So in general, sort of an implementation type flavor. But again, you can imagine circumstances where you could use this as an evocation, for example, right? You have the subject doing some task, and you look at the correlation between these two areas, and when you see it go up, you'll say, oh, okay, that was the time when they were trying to bind together what and where information. So you can imagine trying to run that one backwards as well. But in general, this is going to be used in an implementation manner. Okay? Any further questions about this as a technique? Okie dokie. All right, so in just like a final 10-minute kind of thing, I wanted to tell you guys a little bit about perfusion fMRI. And so the reason I'm telling you about perfusion fMRI is, one, because I've been doing a little work with it recently, so it's kind of present in my mind. And two, because I think it nicely illustrates, by way of contrast, some of the properties of bold fMRI and some of the effects that the idiosyncratic properties of bold fMRI have upon experimental design. And I also think that perfusion fMRI is going to be more and more of a technique in the years ahead, so you might as well hear about it now, because it's coming down the road. So what's perfusion fMRI? Well, we've already established sort of the way that bold fMRI contrast works, right? As you recall, you have an increase in neuronal activity, which leads to changes in blood flow. In fact, fairly complicated changes in blood flow. There's an increase in blood flow and blood volume and oxygen extraction and a whole bunch of other stuff that accompanies neuronal activity. But anyway, you get vascular changes, broadly stated, and that this leads to changes in concentrations of deoxyhemoglobin, and that in turn leads to changes in T2 star or magnetic field inhomogeneities, which are induced by this. Okay, and then subsequently to the bold fMRI signal. Okay. So what's perfusion imaging? All right, and I should say that since we're here at Penn and we've got John Detra in our midst, you should know that John is really one of the guys who pioneered this as a method. So be sure to give him a pat on the back next time you see him. So perfusion imaging. It's really very clever. So what's done is, so you guys know that blood has to get to the brain, right? And the way that blood gets to the brain is through a couple of major arteries that carries blood north. You've got the carotid arteries up front, and you've got the vertebral arteries in the back. Okay? And so all this stuff obviously has to run through the neck. And what John realized, or what John and his group realized, is that you can actually, in effect, tag blood as it's flowing into the brain and then watch where it goes. And the way you do this is you basically provide a spatially selective radio frequency pulse. And we won't go into how this is exactly done. But you deliver some radio frequency energy with the aim of just exciting protons at a particular location in space. And that particular location being like a slab that's running through the neck. Okay? So what you do is, as this blood is kind of flowing up north towards the brain, you basically excite protons in this location and move them into an excited orientation, okay, and into the higher energy state by delivering radio frequency energy at this point. Okay? Then you sit back and you wait a moment, because in a couple of seconds, all this blood is going to come on up here and perfuse into the brain. Okay? And so then, after waiting a moment, you in effect read out the effect of this, this excitation of the protons at these locations up here. We, again, won't get into the details too much of how this is done. But the basic notion is you're able to tag inflowing arterial spins and then read out their quantity up here in the brain, okay, after a brief delay. All right? And by looking basically at sort of the concentration of the number of these spins that are located at this location, you get a measurement then of CBF, or cerebral blood flow, the amount of blood that flowed to that location per unit time. Okay? So that's sort of the broad outlines of the technique. So since we know there's neurovascular coupling between neuronal activity and blood flow, it might be the case, and indeed it is the case, that in locations where there's increase in neuronal activity, there's an increase in cerebral blood flow, and you can measure that. So you can use perfusion fMRI as a neuroimaging method, which is kind of neat. So what are some advantages of it? Or why would you even want to bother doing this? So the first thing is that the way that perfusion fMRI data are actually generated is as follows. You acquire one image. So for your first TR, so TR1, you acquire this image where you label all these little spins and you let them flow up into the brain. But then the very next image, you do your labeling someplace else, like up here where you don't think there's any blood flowing. Okay? So you do sort of a fake labeling. All right? And then you read out your measurement. And the effect then of having done this labeling on the blood flow is obtained by subtracting these two images. Okay? By taking the difference between this label and control image, you're left with the CBF image. Okay? And if we're doing this in a functional MRI mode, what we do is we actually acquire these pairs of label and control images over and over time. Label, control, right? Over and over again, and then generate the commensurate CBF images. Okay? And to make a long story short, one property of taking the difference between adjacent images is that you remove or subtract that 1/f noise. I won't get into why this is, but if you look at the power spectrum of these CBF images under the null hypothesis, the power spectrum looks like this. Ah, what a glorious sight. White noise. White noise. The source images up here, of course, have this ugly, bad old 1/f. But down here, it's white noise. Okay? And again, we don't need to get into why this is. But the implication of this is quite great. So what are they? So number one, because you have white noise down here, this means that you can do away with all this crummy, complicated statistical stuff that we've just spent the last 3 days talking about. Okay? You can analyze perfusion fMRI data using any kind of parametric or non-parametric statistic that strikes your fancy, because it's independent observations under the null hypothesis. You can do permutation analyses of these kinds of data. You can do, Kolmogorov-Smirnov analyses, whatever you want. So it means then that, number one, you break away from an awful lot of statistical encumbrances. But more significantly, one consequence of using with perfusion images is that you don't have to deal with this noise at very low frequencies. So that means it's now possible to detect slow changes in neural activity. Okay? So if you were looking for a change in neural activity that evolved over like a 5-minute period, suppose there's a little area of the brain that slowly increases neural activity over 5 minutes. That would be impossible to see with BOLD, because that slow increase over 5 minutes is way up here in the super high noise area. You just couldn't distinguish your slow change in neural activity from just random noise that's present in BOLD data. However, in perfusion data, that's perfectly observable. It's very easy to see slow changes in neural activity using BOLD fMRI. In fact, J.J. Wang, also here at Penn, did some work where he put someone in the scanner, and on day 1, they sat in the scanner and they tapped their fingers. Okay? And then they went home, they had a nice dinner, took a shower, they came back the next day, and they sat in the scanner for 5 minutes and didn't move. And then if you look at the difference between the images on day 1 and the images on day 2, you find the difference right up here in primary motor cortex. Okay? So you can look at such a long sort of time, the image is stable enough over time that you can actually sort of compare neuronal activity on one day to neural activity on another day and make inferences about the differences between them. Okay? So this is great for things like slow learning and habituation and drug effects and the effects of psychotherapy and all this sorts of stuff. And I know folks at the TRC have been very interested in using perfusion and have done so successfully. And Martha Farah and folks that she's affiliated with have been doing work using psychodynamic and cognitive behavioral therapy and looking at the effects of data on blood flow. J.J. Wang has studied the effects of motion and stress. Ingrid Olsen, myself, and other folks associated with our labs have worked with slow learning and taken a look at the effects of sort of learning specific tasks over time. And all of that is observable using perfusion fMRI and looking at these slow changes in neural activity. So this, I think, is a technique that, for these particular sorts of questions, is available now and is useful. And I think as time goes on and as perfusion fMRI becomes more powerful and develops as a technique, it's probably going to be useful for other sorts of things that we normally use BOLD fMRI to study. All that being said, current limitations of perfusion fMRI right now are the following. Number one, it has pretty crummy temporal resolution. So it takes, actually, instead of 1 second to get an image like this, it typically takes 3 seconds to get a perfusion image. And you get one image every 3 seconds, a label and a control image. So by the time you subtract these images, the CBF image is actually representing a 6-second period, which is, pretty low temporal resolution. So this is not the ideal method to study rapid event-related fMRI. Okay? You can if you want to, but, it's like, why bother? It'd be all the benefits of masochism without, any sort of real improvement. So so bold fMRI continues to be what you want to use for rapid event-related, simply because this is such a slow thing. The other thing is that the spatial resolution is somewhat reduced. You have to get fairly thick slices. So our slices, instead of being 3 millimeters thick, are more like 8 millimeters thick. Okay, so your spatial resolution in the z direction is also reduced a little bit. But all that being said, this is a technique that, under the right circumstances, can be pretty useful for certain neuroscientific questions. Oh, and I should also mention Dan's doing an awful lot of work with perfusion as well over at CHOP. Yeah?
What's wrong with using gadolinium or using a contrast agent that is not endogenous?
Yeah,
Is that impossible?
So Dan Langleben back there asked a pretty astute question, and that is, look, what's being done here is with radio frequency, you're essentially labeling or creating a contrast agent in the brain. And this happens to be a non-invasive contrast agent, and the contrast agent is your own blood, which is kind of a nifty trick. But it's just basically still acting like a contrast agent. There's lots of other contrast agents that exist in fMRI, one of them being gadolinium, which is an element, a metal, which is inert as far as the body is concerned. You can inject it, and it then flows into the brain. And at those locations where it collects, you can sort of measure blood flow, and you can use it for arteriograms and other sort of things like that. So yes, and in fact, the very first fMRI paper ever published by Bellevue and colleagues actually used gadolinium. They did a gadolinium scan while someone was looking at flashing lights in a gadolinium scan in the dark and showed the difference was in occipital cortex. That being said, it's kind of cumbersome to use as a neuroimaging technique like this, because if you wanted to do it over time, you'd have to be able to imagine inject gadolinium for 3 seconds and stop for 3 seconds, inject gadolinium for 3 seconds and stop for 3 seconds, and then also wait for it to kind of clear out. So you'd have to imagine hooking someone up to a gadolinium infuser, which does like a rapid push of gadolinium into their carotid artery and then stops for a moment. And, like college students would do a lot for $20, but that might be a little bit much. But yeah, but if you drip it, then it's just continuous over time, and you won't be able to do a difference between adjacent label and controls.
You do have to copy changes as you're going through the process.
Yeah, but you'd still be stuck with 1/f noise then under that circumstance, because you're not taking difference in images. But in general, though, the notion of using tracers is a good one, and there's work going on using. I guess I wish John was here. There is another sort of molecular species, which is work is being done with. You inject this thing, which I can't remember what it is, and it basically like gooses up the effect of changes in local vasculature. I can't remember what the heck this thing is. It's like molybdenum, whatever. That thing, like one of those things that can be used in a tracer in this manner. And I know that it's something that certain folks are working on. And if I can remember the reference or come up with it, I'll let you know about it. But yeah, so using other sorts of exogenous contrast agents and things to kind of boost up the neurovascular change is something that people are studying. It turns out that gadolinium in this circumstance just isn't particularly practical, but there might be other things like that.
I saw recently, sorry my voice,
Yeah.
that caffeine can boost contrast.
Okay. And
Is that caffeine? Do you know it?
oh yeah. Oh right. So there's
Boosting contrast.
yeah in the general topic of boosting sort of the neurovascular coupling. There's lots of things you can do. Anyone who's kind of gone through medical school, and particularly a neurology residency, will know that there are certain things that affect cerebral blood flow, right? So the relative concentration of oxygen and carbon dioxide in the blood affects cerebral blood flow, and when you're trying to reduce blood flow to the brain, you can have people hyperventilate and all this sorts of stuff. So there are ways to sort of increase the amount of neurovascular coupling, and one of them is by altering gas balance that someone inhales. The other thing that can be done is have them drink caffeine. So it turns out that studies have been done that show that the magnitude of effect that you get between sort of lights off and lights on is increased in those subjects who have had some caffeine to drink. And who knows precisely where within the neurovascular coupling cycle caffeine is having its effect. But it does indeed seem to have this effect. So I mean, actually, most subjects I put in the scanner, I try and have them drink a cup of coffee before they get in there for two reasons. It keeps them awake, and it boosts up this effect. So, I don't know, we might have to sort of officially run it by the IRB if we do this as sort of a consistent thing, but it's not a mistake to have someone drink a cup of coffee before they get in the scanner. That's for sure. Everyone's like, yeah. Mocha latte grande for each scan. Now, absolutely. So finally, there's a way of justifying a grand expenditure of like one of those nice like bean grinding espresso makers you might get in the lab. All right. So we now move to the. So any other questions about this stuff? Yes.
On your list, can you comment just for a minute about the use of patient population?
Oh yeah. Okay. I put that on my list, but I didn't talk about it much. So patient population and neuroimaging experiments. So this is a tough topic. So I alluded to before when I was talking about localization experiments that that the modes of inference of neuroimaging experiments and lesion studies are generally quite different. And that is that if you have a neuroimaging study that shows activation at this area, what you're allowed to conclude is that cognitive process X produces activity at that area. And maybe even under some circumstances, you might be able to further work that up to this area is performing some computational process which is of interest or relevance with cognitive process X. This might be as far as you can push it. Whereas a lesion study lets you draw inferences of the kind of region A is necessary for cognitive process X in the sense that I cannot do this cognitive process in the absence of a functioning area of that brain. So in general, then, the sorts of questions that people ask using patient populations in classic neuropsychological experiments and neuroimaging experiments, they're kind of different. The inferences you draw are a little bit different. So, but nonetheless, in the early days of neuroimaging, people spent some time putting subjects in the scanner who had holes in the brain, and then would do neuroimaging experiments on them, and then attempt to interpret the results. Okay? So, and just by way of preamble, let me say that there are ways of doing patient studies in the scanner which are good and which can lead to good inferences, but they're hard to do, and it takes some time and some thought to do it. And there are lots and lots of really bad ways to do neuroimaging experiments using patients. Okay, so let me give you an example of kind of a bad way of doing a neuroimaging experiment, or at least one which I think leads to not much in the way of neuroscientific gain. So, imagine you have a patient with a lesion in dorsolateral prefrontal cortex, and they're impaired on the cognitive process of working memory, like they suck at doing working memory. So you put them in the scanner, and you put some stimuli up in the screen and say, hey, you, do some work in memory, okay? And you present them with stimuli to be remembered across the delay. And of course, they're abysmal, like they do horrible. And then you go and analyze the data after, and you say, okay, well, here's the working memory condition, here's the control condition. Where was their activation? Well, clearly, there will not be activation in this area where there's the hole, right? So in the area where there's gliosis and no brain left, you're not going to find any activity there. So imagine you see other activity. You see some activity here, and you see some activity here, and you see some activity here. Okay. So what can you conclude about that activity? So are these areas of the brain activated by the cognitive process of working memory? Well, maybe, but the subject wasn't really doing working memory. They were, very poor or impaired at that task. What were they doing? They were probably sweating profusely during the working memory component. They were probably like cursing the day they ever stepped into your lab and got put into the scanner. They were, whatever. They were engaging in a bunch of mental operations, which may or may not have been the one particular thing you're trying to control. So I think that when you have sort of these cognitive subtraction methods run into patient inference, you take sort of all the weaknesses of cognitive subtraction and then add on to it the additional complexity afforded by having a subject who has an altered mental operation to begin with, and you're left with like this really mushy inferential soup. It's very hard to kind of know what to pull out of this. Now, that being said, so this is obviously something that maybe at least in retrospect you shouldn't have done. But there are plenty of ways of doing patient studies that might be more informative. So let's imagine you have a subject so imagine you do neuroimaging experiments, and you find this is the area that's always activated by working memory. Okay? Now you find, or suppose you have these two areas that are always activated by working memory. And now you find subject X who has a hole in their brain right here. And they can still do working memory, right? They can still do the task. Well, now we have an opportunity for some inference, right? Because here's someone who is still able to perform a mental operation despite lacking an area of the brain that you've seen activated previously. Put them in the scanner. They do the mental operation. You're now a little bit more secure in the inferences afforded to you by cognitive subtraction design. That is that activation in a particular location is the result of cognitive process working memory. And you see that they now have activity here and here. You say, oh, okay, this is very interesting. They have the preserved ability to perform working memory, and they have neuronal activity at these areas which are perilesional, kind of right around where that lesion was. All right? So I'm going to make the inference that adjacent areas of cortex took over that function of working memory that is now preserved in this subject. Or who knows? Maybe you'll find. Whoops. Yeah. I can't do it. Yeah. There we go. Good. That maybe you'll find there's activation at the other side of the brain instead. Okay. In which case you'll say, oh, homologous areas in the other hemisphere active. Boy, that was a lot of drawing work for a very small point. But anyway, so in any event, so you can imagine inferences of that kind. And so if you're going to spend a lot of time thinking about doing patient studies, I would recommend to you some writing that Kathy Price has done. She's at the FIL in London. She actually has a chapter in that Feinberg and Farah behavioral neurology book that I mentioned, which comes right after my chapter. And what she talks about there, which is quite neat, she applies some terms. She kind of creates a taxonomy of different kinds of experimental designs that one might perform using patients. And she refers to such things as dynamic diaskesis, and she talks about degeneracy and redundancy. Nobody can read this, I know. So degeneracy and redundancy. And so she kind of describes like different ways that that mental operations might recover from lesions, or that lesions and mental operations might interact, and that it's possible to use neuroimaging to start to try and tease apart these different circumstances where you either have recovery of function at a different location, or you have a backup area that now springs to life, and this kind of thing. And so those are kind of the I think there are, so just to summarize, there are ways of doing neuroimaging studies in patients which are well formed. You just have to be very open-eyed about the inferences you're going to draw when you go into doing the experiment. Yeah?
Do you have to worry about the size of the lesion and the fraction of artifacts in the air?
Oh, right. Yeah, I didn't even talk about that. So another.
So what's your limit? What's the upper bound?
Yeah, well, even just more. The question was, do you have to worry about the size of the lesion and how that, can affect your bold fMRI signal, and because you get air, concentration of the magnetic field lines, air tissue interfaces, and stuff like that.
Particularly the part you were saying, finding activations perilesionally.
Yeah, right. Yeah, so, all the caveats apply of sort of motion. If there's motion and there's a lot of subject motion that can create artifactual signal right at high signal boundaries, which could be like at the edge of a lesion and not. And yeah, so it's kind of tough to provide like general thing, but just to give a general warning, another family of general warnings about patient studies or drug manipulations and things like this is that you have to watch out for any time that the patient population has a change which is confounded or which confounds neurovascular coupling. Okay, so or bold fMRI imaging inference. So one example that was just provided here is that if you have a big hole in the brain at this location. Well, actually, that's going to be filled with fluid anyway. It's going to be like gliosis and stuff. But imagine someone had like a penetrating skull injury, and you just happen to go and scan them like while they're down in the trauma area with like the machete still poking out or whatever. Oh no! Well, it's one of those new cosmetic clay knives. Anyway, but so you can imagine if you had an air tissue interface or an area of high signal boundary, that motion here could create artifactual signal around the edge. So those sort of things apply. But I think perhaps more realistically, another sort of concern that exists is that the basis of these techniques are neurovascular coupling. Neurons increase activity, blood flow increases, we look at the blood flow. Well, what if the patient population has some alteration in neurovascular coupling? So what if you want to study like people who have had strokes? Well, people who have strokes probably have a lot of atherosclerotic disease. What if atherosclerotic disease in the hemisphere where the stroke occurred also impairs neurovascular coupling, such that you get less change in blood flow for any unit change in neuronal activity? There's a puzzler. How about this one? You want to study the effects of estrogen upon cognition, right? So you have elderly women or whatever, postmenopausal women, and you give one population estrogen, and you give another population some placebo, and you're interested in the effects upon working memory, and you want to see like what is the neural correlate of improved working memory in the group that receives estrogen. And so you do this, and you find like increased neuronal activity in some area. But what if estrogen alters neurovascular coupling, which there's some evidence that it does, that it changes the responsiveness of blood vessels to any unit change in neuronal activity. So then you have a confound between your drug changing the neurovascular coupling and maybe changing the mental operations that are really what's of interest. So these are all sorts of families of concerns that you might have. in general, one way out of this thicket is to come up with control tasks that you think would not be altered by that state, right? So in the example of postmenopausal women receiving estrogen, if you could show that, for example, flashes of light and finger tapping exercises evoke the exact same amount of bold fMRI signal change in both your treated and your control group, and then you show that working memory evokes different amounts of neuronal activity in your treated and control group, then you can say, well, it's unlikely to be a general neurovascular coupling effect because I saw this change or this effect of estrogen only in the group, only with the working memory task, but not for sort of these more early sensory motor effects. Okay, so that's sort of one class of sorts of solutions you might apply to that kind of thing. Okay, yeah?
Are we moving on to the next topic?
We're now officially in question and answer session.
Okay, so I was wondering if you can say a few words about just reporting effect sizes in papers. In some papers you read report, say, percent signal change, and other papers you read report effect sizes in terms of t-values.
Right.
Can you just say a few words about relative merits of each?
I've given up and just percentage change now. I just present percentage change. So the question is the following. When you start to take data across subjects and combine data across subjects, is this what you're referring to? Yeah, when you combine data across subjects, do you take like a percentage change effect from each subject? Or, as some have advocated, do you take a t statistic, which is the statistical effect of your task in each subject, and then do a statistic upon those statistics, like do a t-test upon the group of t-values, one that came from each subject? It turns out, for reasons that are probably too long to go into right now, that there are these, I mentioned there are these scaling effects in bold fMRI data that can scale up both the signal and the noise from scan to scan and from subject to subject. It turns out that from a purely theoretical standpoint, the best way to fix those things is to scale by the error term, which is what a t-statistic is. So doing a cross-subject analyses using a t-value from each subject might be theoretically optimal. However, there's this very entrenched mentality in reviewers of neuroimaging papers that there's something weird and illegal and immoral about doing statistics on statistic values. And so I've banged my head against this wall one too many times. So now I just do I've given in. I take the percentage signal change from each subject and then do the random effects analysis upon those values. The reason it's not so much of a cop-out is because percentage signal change also fixes this scaling problem. Perhaps theoretically not as perfectly as the t-value, but close enough that it's good enough. So that's what I do.
Just more for practical reasons.
Yeah.
One over the other.
Yeah, because as a whole, the community has moved to reporting percentage signal change, and I want to be one of the gang, so I present for signal change too. Yeah.
So, sorry again, my voice.
Mhm.
This is in the category of how can I eat my cake and have it too? With our studies, where we have patients responding to cues for drugs that they desire and for other natural rewards, you expect that there might be really fast things that happen, and also there are really slow, sustained things that happen. So, our humble solution to this has been to do sort of bold experiments to look at very brief things, and perfusion to look at the sustained things. But these are separate, little paradigms within a person, perhaps over time with it. It would be lovely to be able to have everything in the experiment, so that you really could have a time course in perfusion that was sensitive enough to let you look at really fast things, or bold things that could go on long enough to let you look at sustained states. We saw a paper, Daniel found it and noticed it in Science a few weeks ago, where they were talking about reverse regression, reverse correlation techniques, where they actually had time courses and showed how, to a visual stimulus over time, that their patients were clustering together, and it was bold analysis. And they just casually referred to the fact that they'd used sort of a high-pass filter and that basically everything was okay. And they seemed to sort of get rid of the 1/f noise problem just with a sort of a move of their hand. And they showed little time courses that looked sort of intriguing to us because the stimuli were minutes long. Do you know anything about that approach? Is there a way to eat my cake and have it too, to look at fast changes and minutes long ones in the same experiment without having to do little experiments?
So the question is there a way that you could either make bold more sensitive to longer time scale, by long time, make bold sensitive to long time scale neuronal changes, and or is it possible to have perfusion sensitive to more rapid changes in neuronal activity? So I'm not familiar with the paper that you're describing, though. I should go take a look at it. Yeah, what's that?
It's a Clint Eastwood movie.
Oh, the Clint Eastwood movie. Oh, yeah, I know all about that one. Okay, good. Well, that's easy to explain. I was worried this was going to be I wasn't going to know what the hell was going on. Yeah, I know that paper. So that paper, the Clint Eastwood movie, just so everyone knows, the experimenters put subjects in the scanner, and they had them watch a clip of The Good, the Bad, and the Ugly. And what they showed was that across subjects, you got the same pattern of neuronal activity across those different groups. Okay? So granted, they were watching a clip of a movie that was several minutes long, but they weren't looking for changes in neuronal activity that slowly evolved continuously over several minutes. Instead, what they said was, here's this movie clip of The Good, the Bad, and the Ugly, and here's when Clint Eastwood's face came on the screen, and here's where that like evil bandito came on the screen, and here's where Clint Eastwood sneered at him, and here's where the evil bandito like fell down dead. And so at each point, there was a face on the screen. Here's the sneer, and then and so here's the guy dying, right? So, but at these particular points in time, a face was presented. Okay, yeah, and actually though these events are happening at relatively higher frequencies, right? You can imagine experimental films, right, that you might go see down like like at the Roxy that you could not use for this sort of thing, right? Where it's a picture of a desk sitting in a room, and like the camera just lingers on this desk there for hours, and then maybe slowly the desk moves across the room to some other location, right? Right. So if that was the experimental film that the subjects were watching in the scanner, that would be a disaster because there really wouldn't be any higher frequency stuff. But luckily, in The Good, the Bad, and the Ugly, there's rapid changes in visual impression. They move from here, they look at this, they do that, and that's what's being detected.
So when they looked at these correlated time courses, because they had their a priori regions, like
Right, sure.
face, et cetera, and they showed how the subjects clustered together and peaked around, and they even made their own little film where they actually sort of took out places and building and things. So I mean, obviously we could do something like that with a drug-related stimulant, but it just doesn't speak to the issue of the longer sustained homogeneous state.
Well, they didn't detect a longer sustained homogeneous state.
No, I'm still asking about.
Oh yeah. But now having dispensed with this science paper, there is a way for you to have your cake and eat it too, and here's how. So,
thank you.
oh yeah, this is going to be pretty cool. You're going to like this. So I talked about perfusion fMRI before and how it's the difference between adjacent images, right? You have the label image and you have the control image, and you're taking differences between these pairs. Okay. What I didn't talk about, or actually though I did refer to it by putting a little graph up here and showing that there's 1/f noise up here, but in the CBF images down here, the noise is now white. Right. So these are the CBF images. What are these things up here? I never really told you. Hey, they're bold images. So what you could do is actually you can have subjects do an experiment, right? Collect data just like this, right? Where every other image has a label applied to it, and then analyze the unsubtracted data as bold data looking for rapid effects, and analyze the perfusion data looking for slow effects.
Actually, GG's current sequence has bold nested within the perfusion, right?
Well, yeah. So I mean,
So it's actually possible to
oh yeah, we've already done it.
analyze our data that way.
Yeah, so we've already done it.
I would really like to do that.
You go, girl. I mean, you can do it. Yeah, I mean, so the data as it comes off this, I mean, it's just bold data in the way that it's normally collected right now.
So I've asked this question a number of different ways, and this is the 5 minutes of data. It's perfect.
There you go. So good.
Thank you.
You're welcome. Yeah, so that's a solution for that. You can analyze the bold data directly. Now, it's not a perfect free lunch, and the reason is because, the reason is because to optimize the bold so that you can detect perfusion effects well, this isn't the best bold you can do, right? It's not 100% bold. It's kind of like 80% bold, but 80% bold is better than no bold at all. It's boldish, yeah, bold-esque. So, okay, good. Another question? You got a minute. Who's got a 1-minute question? Dan.
Perfusion images, perfusion data analysis.
Yes.
It's not doable in SPM, right?
You can do it in SPM.
Actually,
Yeah.
Juan has made a program for doing it within SPM too.
Yeah. So.
If you take raw SPM as it is,
Mm-hmm.
without any add-ons,
Oh, let me put it this way.
you need to correct for decay and all that stuff.
Once you have CBF images, you can analyze the CBF images in SPM. But you got to get the CBF images first. So you first need to use a snippet of code under MATLAB or under VoxBo, which does this. And actually, the subtraction is more complicated than what I've described. We actually wrote a paper which is tedious in its details, which describes really how you need to actually subtract these things and align them in time and all the rest. But that code exists. It's under MATLAB or SPM. I think there's even like a little C snippet of code that'll do it. So then once you've got your data rendered in CBF images, then you're off to the races. You can use SPM. And in fact, in SPM, you analyze these images as if they were PET
On
images.
the PET side of the analysis frame.
Is there any other package except SPM or VoxBo that with an FSL that the routine could made?
You could use anything. Once you've got them in CBF images, you could use anything to analyze them.
I'm talking about the step 4.
Oh, then the only thing, you just got this code that JJ and I have written. That's it.
It's not available in the community.
No.
right?
Although it's posted on a website, and we've stuck it on the SPM mailing list. But
And it's pretty transparent. I mean,
Yeah.
Juan used it to
Yeah.
even plop into an SPM2 program.
Yeah,
So-
it's not too hard. You can do it. It's not too hard. All right, guys, that's it. It's been 4